Okay, Lacey, this is I'm going to talk about the second set of notes for section 1, 2. It's the stuff that was on the backside. This is what we did on Monday. So um, I think the backside we got to the end of here, and then we continued on. The video I recorded in class didn't want to upload for some reason, so I'm trying it again. So I have this all filled out already on the note sheet, so I'm just going to go through that with you. But what I did with the kids on Monday is before we finished that note sheet, we filled out a note card that really helped to kind of explain some things. So I'm going to fill out that note card, and I'll kind of show you how this works, and then we'll go over to the notes real fast. So um, when we start studying sequences, okay, there are two different types of sequences. There are arithmetic, sometimes I call it an algebraic, or geometric. Okay, arithmetic or geometric, okay? And arithmetic is when you're adding or subtracting, plus or minus a number each time. And geometric is when you are multiply or divide a number each time. Okay. Now, when you're doing geometric, a lot of times when you're multiplying or dividing by a number, if you're dividing by a number, they will not put it as division. They will write it as like 1/2 or something. So if you're dividing by 2, they'll write it as 1/2, and they'll leave everything as a multiplication. Okay, so arithmetic, geometric. All right. Now, when you are doing arithmetic and you're graphing it, it will look like a linear function. It will go up by the same number every time. When you're graphing a geometric, it will be an exponential function. So this guy will look like this when you graph it. It will go up exponentially. This guy will be a linear function. Will look like that. Okay, like a straight line. Okay, so there are, if we're writing an arithmetic, an equation for arithmetic sequence, there are two different ways of writing it. You can write the recursive formula, and you can write the explicit formula. Okay, recursive and explicit. Okay, so given the scenario for arithmetic, let's say that I am trying to add 3 each time, and my first number is 2. Okay, let's just say that that's that scenario. For the recursive formula, you are not taking into consideration the first number at all. Okay, the recursive number, or the recursive formula, just talks about u sub n in terms of the one right before it. So you are adding 3 to the number before to get u sub n, okay? And the number before u sub n is called u sub n minus 1, okay? This is saying I'm taking the number before it and I'm adding 3, and that's it. That will give me u sub n, okay? It is not taking into consideration the 2 at all. So the recursive is nice because it's not got that confusion in the equation. The equation is pretty easy to manage, but the problem is if I want to know like the 52nd term, I have to know the 51st and the 50th and the 49th and the 48th. I have to know every single term leading up to the 52nd term. Okay, so rather than doing that, if I want to know the 52nd term, a lot of times I'll do the explicit formula, okay, which looks kind of like u sub n equals m times u sub n minus 1 plus b, or y equals mx plus b. So if you like the u sub n's, you can use the u sub n and u sub n minus 1, and you can use y and x instead. It doesn't matter. So this m is going to refer to the number that you're adding or subtracting each time, and the b is going to be the first number. So for the scenario that we had up here, what our explicit formula is going to look like is y equals, we're adding 3 each time, it's going to be 3x plus 2. So now this formula is already embedded in there that I am starting with the number 2. Okay. Now the problem with this is if I want to know the 52nd number, I'm going to need to plug in 51 instead of 52. Okay, because the first term is kind of labeled as u sub 0, so they basically inserting 0 into this equation. 3 times 0 plus 2 will give me 2 as the answer. So the first term is labeled as 0. The 52nd term would be labeled as 51 is what you would need to plug in. Okay, so that is the explicit formula for an arithmetic sequence. Okay, so let's go over here to geometric. Geometric would be like I am multiplying by 3, and the first number is 2. Okay, multiplying by 3 and the first number is 2. So the recursive formula does not take into consideration what the first number is. It's just saying you're taking the one right before it and you're multiplying by 3. Okay, so this is u sub n is the one right before it times 3. Okay, that's good because it's an easy formula, but it does not tell me where I'm starting from. So if I want to know the 52nd term, I have to know the 51st and the 50th and every number leading up to that. So I would have to know the entire sequence. Whereas in the explicit formula, it makes it really nice. The explicit formula for u sub n is taking u sub, let's see, how do I want to say this? I'm not going to write it with u sub n. I'm going to write it with y equals a b to the x power. I'm just going to write it like that. I'm not going to write it with the u sub n's and all that good stuff. Okay, a is going to be your first number, and b is going to be your number that you're multiplying or dividing each time. Okay, so for this scenario, we're starting with the number 2, and we're multiplying by 3 each time. So that's 2 times 3 to the x power, and that's what he will look like. Okay, now, again, if you're doing the 52nd term, you're going to plug in 51, because if I plug 0 in, that would give me my first term of 2. So 0 is actually reflecting the first term. So 51 would actually reflect the 52nd term, okay? So there's just a little bit about arithmetic versus geometric, recursive versus explicit, okay? So there's 4 different kinds of formulas. Again, these top 2, the recursive formulas, are not taking into consideration what the first term is. This one, I can plug any number in and get the 52nd term or the 117th term or whatever. Now, the last thing I'm going to have on the end of here is that star, star, star. Not every pattern can make explicit formula. So an explicit formula cannot be made from every pattern. Okay, so sometimes you will have a combination of arithmetic and geometric. So maybe you're multiplying by 3 and adding 2 each time. Or maybe you're adding 2 and then 3 and then 4 and then 5. So you're not adding the same number each time. In that case, you probably can't make an explicit formula from it. Okay, it has to be strictly arithmetic and strictly geometric in order for these formulas to work. Otherwise, you have to do some kind of different tricks to it, which we don't talk about in this section. Okay, that's a little bit too advanced for this section. So this is kind of a little bit of a breakdown, and it seemed to help some people kind of sort out their thoughts, I guess, for both of those. In section 1.3, which we started today is Tuesday. I'm recording Monday's lesson Tuesday since the recording didn't work. We started learning arithmetic, and it kind of helped people to already have this note card in place. So I'm getting a little ahead of myself, which makes 1.2 a little bit more confusing, but 1.3 was a lot easier for people. Okay, so there is that. All right, now I'm going to go back to the notes, and I'll share with you kind of what we did on the notes on the back side. So starting with, let's say, starting with example 5. Right here. Okay, starting with example 5. Is salary raise sequence. So if the starting salary for the job is $20,000 and it raises $2,000 at the end of each year of work, what will the salary be at the end of the 6th year? So what this would look like as a recursive sequence is we're just adding 2,000. Okay, u sub n minus 1 plus 2,000. We're not taking into consideration that we're starting with a $20,000 salary. Okay, this is just the recursive formula. If I want to embed that $20,000 in, this is the explicit formula. So exp, this is the recursive. Okay, this one embeds the 20,000 in there. So this is the B part. This is the mx. All right. So u sub n is 2,000. What I'm increasing every time times n plus the 20,000. All right. Then they want to know after the 6th year. So we just went ahead and did a table here. We said year 0 starts 20,000. Okay. Year 1, at the end of year 1 is 22,000. At the end of the year 2 is 24, 26, 28, 30. So at the end of the 6th year would be $32,000 is what they are making. Okay. Again, you could have plugged that in to this equation. Plug 6 in here and added that to the 20,000, and you would have gotten 32,000. Okay. All right, so this next one, example 6, sequence formed by adding a pattern of values. So here, we are, in this example, one chord going all the way across the circle splits it into 2 regions, okay? 2 chords is splitting it into a possible 4 regions. 3 chords is making a possible 7 regions. 4 chords makes 11 regions. 5 chords we had to figure out made 16, okay? So what's happening is here you're adding 2. From 2 to 4 is adding 2. From 4 to 7, you're adding 3. From 7 to 11, you're adding 4. From 11, here you're going to add 5, etc., etc., you're going on. So what you're trying to figure out is what the pattern is, okay? So this is kind of confusing because this is a little bit more than just a regular arithmetic pattern. You're not adding 2 every time. You're adding a different number every time. But what we've found is that in this pattern, u sub n, okay, is the one right before it, but then you're adding n to it, okay? So here, like u sub n, if I'm trying to find the 5th one, okay, that would be like u sub 5, okay? U sub 5 is whatever the 4th one was, okay? U sub 4, that's the n minus 1 part. U sub 4 was 11, but then I'm adding 5 to it. That 5 comes from the n, right? Okay, so it's the one right before it, which was the u sub 4, and that had 11 regions. But then we're adding 5 more to it, which was reflective of that 5, okay? So 11 plus 5 should give me 16. So we kind of did the table here, and we said that 5 made 16, okay? Then I take this 16 and I add 6 more, which is what the n is. N is 6, and I get 22. Then I take that 22 and I add n, which is 7 to it, and I get 29. And I add 8, and I get 37, okay? So I went ahead and changed part B, use a table to find the maximum number of regions formed by 20 chords. We just changed that to 8 chords because I don't want to do all 20. So just 8 would become 37, all right? So in this one, this kind of looks like an arithmetic sequence where you're doing plus a number, right? The recursive formula for arithmetic, but you're not adding the same number every time. You're adding n, and n is what changes every time, okay? So that's where it gets kind of a little bit confusing, all right? The last one, this is like number 16 on the homework, which I think I did with you. This is the chlorine one. So Dr. Miller starts with 3.5 gallons of chlorine, okay? And then each day they're adding 0.25, and 15 is evaporating out. So we're starting with the day before. N minus 1 is always what's before n. So we're starting with the day before, adding 0.25 gallons, and then 15% is evaporating out. But if 15 is evaporating out, then that means that 85% is left. And we want to know what's left. So we're doing times 0.85. So it's whatever it was the day before, adding 0.25 and evaporating out 85. They want to know how much chlorine will be in his pool on the 6th day. Okay? So on day 0 is what we call it, is where we're starting from. That's 3.4. Okay? So at the end of the first day, we're taking that 3.4, we're adding 0.25, and then we're multiplying by that 0.85, and we get this one, okay, this number, 3.1025. Okay, then at the second day, we're taking the day before, which was 3.1025, adding 0.25, and then multiplying by 0.85, and we get this 2.8 number, okay? Then we plug that in here, add 0.25 to that, and multiply by 0.85, we get a 2.6 number. Plug that in, add 2.5 to that, and multiply by 0.85, we get this number. And we keep going until the 6th day. At the end of the 6th day, we get 2.1647. That is how many gallons of chlorine are in the pool. So this sequence is using this pattern right here, the one from the day before, u sub n is the one from the day before, adding 0.25, and then taking that times 0.85, and that will, repeating that pattern over and over again, will give you what this one is. Now, this guy is technically a recursive formula. You know that it's a recursive formula because it does not take into consideration what the first term was, right? The first term of 3.4 was never used in making this formula. And recursive also, in a recursive formula, I also have to know what the one from the day before was. And that's that n minus 1. So if it incorporates the n minus 1 part in there, you know it's a recursive formula because If I want to know the 6th day, I have to know the 5th day, and I have to know the 4th day, and I have to know the 3rd day, and etc., right? This is a recursive formula because of that, okay? So there is that, but since, okay, so given that this is a recursive, since it incorporates both adding and multiplying at the same time, it is both an arithmetic and a geometric. It incorporates both of them in there. We probably can't make an explicit formula for it, okay? Because if it incorporates both of them, it's a little bit more complicated, and you can't make an explicit formula. So we only are left with this recursive, and we have to kind of do this process, okay? Just because the equation is so loaded, okay? So that's the end of the notes. I have this note card here for you, so if you want to take mine when you get back, that's fine. You can have this, or you can rewrite it if it helps you, whatever you want to do. But I will save these notes all for you, and I will give you this note card. So that is all for section 1-2, math patterns. Okay?